One of the best things about using parametric equations to describe motion is that it lets you build complicated motions out of simpler pieces. Let's look at an example. So let's imagine that we have a wheel with radius r that is rolling along the ground without slipping. And let's write parametric equations for the curve traced out by the spot on the wheel that starts on the ground. So we have the ground here and a circle or a wheel with radius r. And what we're going to do is watch this spot on the ground as the wheel rolls to the right. So, at first, it's hard to tell initially if this point is moving right or left, but as the wheel rolls to the right, this point is going to get lifted off the ground, and then eventually it's going to swing over the top, and then, at some point, this wheel is going to complete one rotation, and this point is going to come back down to the ground. And then the whole thing is going to start over again somehow. So it's kind of a complicated situation. This definitely isn't a graph of anything that I recognize, especially because of this weird pointy spot here. But parametric curves still let us build this motion up out of simpler pieces. So how we can build this out of simpler pieces is to break this motion down into the rotation of the wheel and the motion of the wheel relative to the ground. So first, let's just start with the wheel, or the point on the wheel. So the wheel is a circle of radius r, like this. And the point that we're watching starts at the bottom. And as the wheel rolls, the wheel is turning this way. Okay. So the point goes clockwise around this circle. So this is motion around a circle. So we have some tricks for writing down this parameterization. So we're going to use a sine and a cosine, but the radius is capital R, so capital R. Let's see, we want to start at the bottom. So we could so x is going to start out as 0. So maybe we should use sine for x, since that's going to start out at 0. And let's use theta for our parameter. Theta is going to measure the angle that this wheel has rotated. And y, it needs to start big, except it needs to start negative. So we can't just have cosine, we need a negative cosine. Okay, and then just to check, we should check that this is going the correct way around the circle. So we know that this starts at the point 0, minus r, and as theta increases, sine gets bigger and cosine gets smaller. That's actually backward. That's not quite right, because we don't want our x coordinate to get bigger initially. We need it to get smaller because it's supposed to go negative. So it looks like we also need a minus sign right there in front of our x function. Okay, so now we have parametric equations that describe the motion of the point around the circle. Now let's just describe the motion of the center of the circle along the ground. I guess I've set up this coordinate system so that I've put the y-axis vertically here so that y equals 0, that is the x-axis, is the ground, and the initial position of the center of the circle is x equals 0. So this starting point for the center of the circle looks like the x coordinate's 0, and this central point starts one radius off of the ground, so 0, r. All right, now it moves to the right, so what we need to do is figure out, so we're watching this point at the bottom. After the wheel rolls for a while, this point has rotated through some angle, which we've been calling theta. We need to figure out what are the coordinates of this point, of the center of the circle, after the wheel has rotated this angle theta. Well, the center of the circle isn't moving up and down at all. So the center of the circle, its y-coordinate is still capital R. So we're going to be writing this as a parametric equation, and so y is just the constant r. Now we need to figure out, after we've rotated an angle theta, how far has this wheel rolled along the ground? Well, because the wheel isn't slipping, the distance that it's rolled along the ground has to be the same as this distance, this arc that I have in red here. And if you remember about the lengths of arcs of circles, the arc length of the arc of a circle is the radius times the angle that you have rotated through. And so this red distance is just the radius times theta. If you're using radians, right? Theta has to be in radians for this to be true. Okay, so we've described the motion of the center of the circle, and at first we described the motion of the edge of the circle relative to the center. So we can just add these two motions together, literally by adding them. So for the compound motion of watching the point on the rim of the wheel, it's r times theta minus r sine theta. And for the y-coordinate, it is r minus r cosine theta. Okay, so these parametric equations probably aren't what you would guess, but we built them up out of these simple pieces, just a line and a circle. So we can have some confidence that these actually are right. And if you do graph these, you do get this sort of arc that goes up, comes back down, there's a pointy spot, it's called a cusp, and then it repeats. It arcs back up and then back down, and then there's another cusp like this. Okay, this is actually a famous curve. This is called a cycloid. And I think it's one of the best examples of how you can use parametric equations to build up complicated motions out of pretty simple pieces.